So good morning, everyone, and welcome to the last day of CDC 2024. It is a great and distinct honor for me to be introducing the 2024 Bodhi Lecture Prize winner, Professor Carl Henrik Johansson from the Royal Institute of Technology in Stockholm, Sweden. Kalle, he got his PhD from Lund University. He has had visiting positions at a number of universities, so UC Berkeley, Caltech, NYU, just to name a few. As I was preparing these remarks, I got rather almost tired of all the awards that he won, because if I were to list them all, that would be the talk. So instead, a select subset include IEEE Fellow, member of the Royal Swedish Academy of Engineering Science, and he's also the winner of the IFAC Young Author Prize, which it turns out he didn't exactly win yesterday. So I also should say that as I was preparing these remarks, I've actually walked around the last few days asking people for dirt on Kalle that I could share on stage, and I am really sad to tell you that people just said, nah, he's such a good guy, there is no dirt. So, great scientist and good guy. But I can tell you, though, that a few days ago at the banquet, I was standing talking to Kalle, and this person came up to us and said, excuse me, I like to take pictures with famous controls people, so, and then they pushed me out of the way and said, do you mind? And then she took a picture with Kalle. So, great scientist, good guy, and a little bit of a celebrity, it turns out. So I could not think of a better Bodhi Lecture Prize winner. And today he's going to talk to us about transforming mobility through learning and control. Kalle, welcome to the stage.
Thank you. Thank you, Magnus. Thank you very much for that kind introduction. And thanks the award committee. Of course, it's an amazing honor to get this opportunity to talk about some of the stuff that I work on these days. Thanks and congratulations also to the organizers. It's really been a fantastic week here in Milan. And the Bodhi lecture actually means a lot to me. It was more or less the start of my career. I started my PhD in Lund just a couple of years after Günther Stein gave this great lecture, Respect the Unstable. Maybe for the young people in the audience, you're not familiar with that, but that was a lecture where Stein took the example of a very simple flight control system and showed that with Bodhi's integral, you could argue about the fundamental limitation of using feedback to stabilize and handle non-minimum phase zeros. It was very inspirational to me. It was not my idea that I should watch this video when I started my PhD. This was basically compulsory when you were a PhD student in Lund at the time. So we have it, of course, not on online, but you had this VHS cassette and you watched this as a seminar and so on. So the spirit of this time has been with me since then. So my great supervisors, Carl-Johan Åström and Anders Ranser, they were really having this spirit of problems you should work on should be motivated from applications. And good methods being developed should then have an impact on real system. So this is something that I have carried with me in the work that I've been doing in my group. And here I took out one thing that we have been working on and on transportation that I would like to share with you here today. So there are a number of fantastic PhD students, postdocs, collaborators, and so on that have been contributing to this talk. And also some people actually, when I was rehearsing this talk, gave me some feedback of how I can improve it. So with that, I would like to start the presentation. So let's talk about how do we motivate work on transport. And of course, there is many different ways how to do that. So let's take one of them. We want that our children should be able to live sustain on this planet, and we want their children to do as well. So what you see here is the emission of different modalities of transportation. Transportation of goods and people on the roads, on the sea, in the air. And what you have on the x-axis there is from year 2000, and then a projection into the future. So as you see, we really need, and this is what it's indicated here, right? We really need to get the CO2 emissions down. This will not happen automatically. It's basically a task for the students in the room to spend your career in doing this innovation, develop this research that will contribute to this positive development. And I believe very much that control will have a very important role to play here. But let's look a little bit what has happened in the area of transportation. So today, there is not a single automotive company in the world that do not have these three keywords on top of their R&D department. So it's electrification, it's connectivity, and it's automation. If you're interested in doing research in this area in Sweden, it's actually pretty great because we have two of the world's largest truck and heavy vehicle manufacturers in Sweden, so Volvo and Scania. And we have throughout the years now been collaborating with both of them, and you see some movies here illustrating some of that work. So, but let's look back a bit and let's be a little bit critical. So 10 years ago, SAE, the Society of Automotive Engineers, came up with basically this roadmap of how we should go with the cars and vehicles of today, basically human-driven vehicles, to something where we don't have any driver at all, fully automation, level 5. And at the time, there were CEOs of big international companies that says, okay, yeah, let's just do it. And it's a piece of cake. We just solve this problem. It will take a year or 2 or 3 or so, but let's just solve it. And of course, there is great success that has happened. We have large experiments in the United States, for instance, by Waymo. There is a lot of other success stories. You have the videos here from the public transport in Stockholm, and you have some test sites for autonomous driving in a mining operation up in the northern Sweden and so on. So did we solve the problem yet? No, not really. I mean, we don't find that every single vehicle automated. We have these tests going on, but there is also more or less every week happening things. Either if you are working in this domain, you experience things that is happening, or you read about it in the news. I mean, this is maybe not new to this community, or if you are a scientist, because you then maybe think about this problem a bit more systematic and understand that this is really hard problem. So this is a quote of a famous person from Berkeley, Stephen Schladover, who has spent his whole career on automotive vehicle, automating transport and vehicles. And when he was giving a talk in Sweden some years back, he made this quite pessimistic, if you want, or quite serious projection about how long time it would take. So why is it so that it's difficult? Yeah, basically, it's difficult because we have all these corner cases. So for instance, you take this truck that is going downhill in a northern country, a heavy vehicle, slippery condition. Even for this human-driven vehicle, as you see, it's very hard for the human to stabilize that non-linear dynamics. It's really a hard problem. And in Sweden, for instance, we are running this type of winter test and so on. We cannot deploy this technology if they cannot be driving up in the north. In the two videos to the left, you see something else which is interesting. The difference between an experienced driver and teenagers. So on the bottom one, right, you see a London bus driver who have been driving a lot, and he discovers something interesting is about to happen and communicate that in a quite non-traditional way. While the two guys on the scooter there, right, didn't really think what could have been behind that car, and something bad is happening. So why is this a hard problem to solve? Why is it hard to automate? And the argument I would like to make here today is that it really has to do with uncertainty. It does not have to do with better computations or more data, just cranking up the thing. It has to do with dealing with uncertainty in this system. And there are many people in control working on transportation and this type of automated vehicles, right? And for many of us, it's really that control is the science of uncertainty. We are the one who provide these tools that is needed in order to succeed in this domain. So what I would like to talk with you about here today is things that is ongoing right now. I won't talk about old stuff. I will talk about things that excites us as we speak. And I took 3 different case studies on different layers of the transport system. So looking at network optimization, think about the future of transport when we, for instance, consider the whole road network of Sweden and do planning of electric charging over such a network. I will then look at traffic control. How can we use the road infrastructure more efficiently by doing better control of the traffic there? And I will talk a little bit first on vehicle autonomy. So how can we actually make this vehicle succeed, for instance, as you see in this video there, very much by connecting the infrastructure to the vehicles. So building actually more informative control system. So not think that we should just have individual vehicles solving all the problem themselves. We know from a control perspective that this is not a good idea. It's better to utilize more information. So let's start with that one, and let's go back to another pioneer in this area, Pravin Varaya. So Pravin, of course, many of you know, big name in stochastic control, adaptive control, and many other areas, among one, intelligent transportation, automated vehicles, and so on. He came to a workshop we organized in Stockholm 2018 and give a very nice, inspiring presentation. There was an Uber accident in 2017 happening in Temple, Arizona. Some of you might remember it. What happened was as illustrated on the top left picture there. There was an intersection. There was a human-driven Honda, the blue arrow there, that was turning left in the intersection. And then there came a red vehicle, an automated Uber there, into the intersection. There was occlusion in the intersection. You see some snapshots here, so they didn't see each other. But they didn't realize that they didn't see each other. The control system or the automation didn't stop or reason about these things. And in the talk here, Pravin were discussing a little bit different. How can you design intersection in different ways and so on? But what inspired us was actually a more fundamental thing from control. When we think about the environment, how do we represent the environment as states? And if we don't even know if there is a vehicle there or what is there, how do we include that in the state representation and the design? And it's actually, if you think about it, it's fairly straightforward. If you go back maybe 50 years in the control literature, the concept has been developed, right? I mean, it's set-based techniques and reachability. So how you can think about this system, if you are in a T intersection, we sit in the blue automated vehicle there. It's inclusion, we have some inclusion, we don't see what's behind the yellow vehicle. And what can we do? Of course, we can represent the area that we cannot see, the occluded area, but we know the traffic rules. So what we can do is now that we can propagate what we don't see as if there were something there. So we could, for instance, do that in a robust, a worst case type of analysis, propagate that forward, or we can do it in a stochastic setting where we take the probabilities of how that area is going to move. The nice thing with such an approach, such a set-based approach, is that it's modular. So if you now connect the infrastructure, so you have your own sensors, but you have also a roadside unit that sits on a house there that can see behind what the car cannot see, you can communicate this type of sets and integrate that into the same picture, and you can use that now in this vehicle that is reasoning about if it can go or not. So you see the idea here is very simple. So you basically built an architecture where an individual vehicle now fuse information from other roadside units, from other vehicles, and then it predicts forward how is the scene evolving, taking vehicle dynamics into account, but also assumptions on things that it does not see, and then based on that, you find safe trajectories, and you can optimize these type of trajectories. So this is I want to highlight that this is a problem which is not much implemented today. So I want to show a little bit the implementation of what we have, but I think it's a rich problem that have much more to do also from the fundamental side. So I'm going to go into showing some simulation and some experimental work now, but it's really, I think there is much more to be done here. So this is just illustrating a little bit the same thing in a different setting here. So we come again in that automated blue vehicle into an intersection. Now, depending on the sophistication of the information that you have available and how you reason about that information, you get different type of conservativeness of that automated vehicle. So you can think like in the top of these 4 rows of different scenarios that we go through, in the top one we have only the onboard sensors. And you see the dark color indicates that you don't know what it's behind. In the third column instead, what you have is that you have shared information, and with this shared information now, you can reason much better and have a less conservative trajectory, and in the best situation, which is on the bottom one, you progress much faster and so. But let's leave a little bit that setup, and let's look how it works in practice. So now we don't have a blue car any longer, we have a big white truck. So we are sitting in this automated truck that is waiting here in this T intersection at the Scania test tracks outside Stockholm. And then there was another truck, as you saw, passing, and at some point this truck is turning out there. Maybe not too exciting to see this drone video there, but let's look behind the curtain. What is going on in this picture? So what you see on the bottom 2 plots is 2 different snapshots of the sensor information available in that automated truck. So the green stuff that you see in bottom left is a LiDAR scans from the truck itself. And then the blue thing is from a roadside unit that helps that truck getting information around the corner. And then the truck fuses that information, and then the color coding is, so to say, in the system that is running on board the truck, in the navigator and the planner, the motion planning in the truck. And the color coding now means information about if there is something on that lane, or if I don't know, or if I think that there could be something because in the past there could have been something that I was not seeing. So that was the first piece. So now we switch gear quite dramatically. We will talk about how to use machine learning techniques to do traffic control. So the second problem here comes from some other work that we started some 15 years ago or so. We worked a lot on truck platooning. We developed a system to run this. You see some tests here that we are doing in Denmark and in Sweden. So basically, automated truck platoons so they can travel on the highway like this. So while we were doing that, we were thinking about the problem here that you maybe see in some of these videos, that the cars are passing the trucks. So trucks in Sweden go 85 kilometers per hour. Cars go 110 or 120 kilometers per hour. So what happens here is that the trucks or the platoon here are acting as a so-called moving bottleneck. So if you think about it, on the cartoon on the bottom of this slide, you see a single truck. For the cars that are passing that single truck, it is as if the highway do not have 3 lanes, but it has 2 lanes. While if you are further to the right, you see that there is like 3 lanes, so it's a higher throughput there. If a situation appears like it is here, so further to the right, downstream, there is a congestion. You can imagine that you can now do a little bit of regulation, slow down the cars a little bit with these truck platoons in order to mitigate some of that congestion. So that is an idea that we got quite excited about, and there is other people here in the audience also who have been working on that. So let's go a little bit more into the detail of how this is done and what is the mathematical models behind. And let's go back to some high school physics here, so to Euler and Lagrange. Euler, when he derived the fluid of motion, he was thinking about the fluid through a pipe. He made a cut in that pipe, and then he derived the equation of motion by considering the fluid through that cut. Lagrange, on the other hand, did something different. He considered a small parcel of that fluid, and then he said, let's see how that evolves some delta t forward in time, and then he derived his equation of motion. So what does this have to do with traffic flow now? Yeah, basically, traffic flow, according to Euler, is the traditional way of doing traffic control. So we have sensors in the infrastructure, like these gates that you see here on the picture, where you have sensor measuring the density and flows passing by them on the highway. Actuation is typically something like this digital road sign, where you suggest to the driver what speed they should be keeping. So that is traffic control according to Euler, and this is a lot of work of how to do that in a more efficient way, and so on. Traffic control according to Lagrange. What does that mean? That means that, okay, in any single vehicle today, you have a mobile, or you have a built-in system in the vehicle, so it knows where it is. So that would be the sensors, if you want probe vehicles or mobile sensors that we have. An actuator in such situation could be that truck that you see in the picture. If we now automate that and that is connected, we could regulate the velocity of that truck. So you see, in this case, we get a control system which looks something like this. So we have some red vehicles that we can measure the density and flow perhaps around this vehicle. We bring that measurements in, and then we base control action on that information, which could mean that we are controlling the same vehicle that send this information to us, like in the picture here, or of course, these can be separate vehicles if you want. So let's see how this can be done, and let's see some work, particularly that we have been doing about this thing. So here it's a little bit more detailed picture, right? So what we need to do, of course, we don't know the dynamics of the road traffic. So we need to build that model online. So what we do is that we learn that model out of measurement. And out of that learned model, we try to reconstruct the state of the highway on that segment where we are, and then we use that to predict forward in time what is now the state would be a little bit ahead. And then we use that prediction to now take control action, maybe increasing the speed of this vehicle a little bit or decreasing the speed of them a little bit. So let's go into some detail in the mathematical modeling. So sorry for you who are in this area, this will be very, very basic. So there is two types of model if you simplify world a little bit here in traffic control. Either you have macroscopic traffic models, where we think about the dynamics of individual vehicles. Or we have macroscopic traffic models, where we think about density along the road. So a continuous variable in time and space. If we model now individual vehicle in the microscopic traffic model, it means that we just tell what velocity each individual vehicle has. In the macroscopic model, we have the evolution of the density along the road. That is the celebrated LWR model, something like this or something more complicated than this. You see there is a velocity function, a map v here that pops up. And that's the same v in both these pictures. So in traffic theory, they call that the fundamental diagram, or actually not exactly the velocity. They take the density times the velocity, so the traffic flow on the y-axis and the density on the x-axis, and consider that. And in the simplest setting, that has a shape, this triangle shape, where if you have zero density, you have zero traffic flow. If you have too high density, you have zero traffic flow. And then you have a linear increase until you come up to the capacity of the highway, and then it decreases again. So this is not only a theoretical construct, this is very similar to what it looks like in practice. So this is experiment we did on the highway south of Stockholm. Actually, we were out there driving our trucks for months, collecting data and so on, and then we just look at the data. So the data here actually come from the existing infrastructure, in this case, that we have on the highways, where we get real-time data. And you see that, to some extent, a little bit for lower density, it reminds of this shape. For higher densities, we are all over. But this is what it looks like. But let's come back to the problem we were interested in. We were interested in a problem where we have cars, and then we have a few connected automated trucks or other type of vehicles. So if we now represent that, that would be a model where we have that PDE model representing the density, and we then have, in this case, capital N number of ODEs describing this individual vehicle. So this is a very interesting object to study, which mathematicians are studying. People from this audience is studying. Dele Monash, who sits just here in the audience, did her PhD on this topic. So a lot of interesting phenomena can happen in this, and we need to understand when this is well posed and so on. Here we will just look a little bit using that model and see what it looks like, and then come back to the training or system identification part. But let's look at what characteristics this type of model have. So we have n number of connected vehicles. So these red vehicles, they generate these black trajectories that you see in this plot. So in the plot there is time on the x-axis and its position on the y-axis. So you see the red vehicle are passing through, so to say, the highway there with some distance in between them. The color coding is the density. So more reddish color means that there is a higher density of vehicles. A more bluish color means that there is less density. So the problem we are interested in, I talk about model learning. So the problem we are interested in is now, how can we from data of these red vehicles now learn a model so that we can reconstruct the density all over that square? So what's the question I'm interested in answering? I'm saying that I get now data from the individual vehicle. So I get the position of the vehicle, xi. I assume that the vehicle can sense the density around them, rho I, and that they know their velocity, vi. So we have n vehicles that provide that information. Can we, out of that information now, estimate the density rho hat? So let's try to do that, and let's try to do that with neural networks. So what we do here is that we form two different neural networks. So the first neural network is a map from time and space, t and x, to the density rho. And the other map is the velocity map, so from rho to v. So how would I solve this? So if I didn't take a class in control now, I would just, of course, apply my favorite machine learning technique. So I will basically train the neural network by minimizing these two cost functions that you see on the bottom here. So train the parameter in these neural networks. So this will not work. This will give you rubbish. You cannot use that. So of course, what you need to include here is physics. So what you do is that you now impose that it needs to fulfill that PDE that I showed you, our trained model, and then I put the constraints also on the velocity function because I want that to be a concave function. So I impose these two constraints, and if I do that now, I can formulate a training problem which is give me something interesting. So I basically would like to find this. I want to solve this problem. I do Lagrangian relaxation of that problem, introduce a Lagrangian function L here that depends on the parameters of the two neural network together with the Lagrange multipliers. So such an optimization problem we know how to solve. We can, for instance, solve it by introducing the primal and dual problem here, right? Where the primal problem corresponds to the parameters of the neural networks, and the dual problem corresponds to learning the multipliers. So this we now solve. We solve it with standard gradient descent methods where we iterate between the primal and dual. Actually, in practice here, it shows up that you do one primal step and then you do multiple dual step. There is a few more things you have to think about, as I mentioned here. The sampling of these integrals that you have in the constraints there will be important. So there are some tricks one have to take into account. But basically, it's a fairly straightforward way of trying to train this system. So how does it work now on, so to say, real data? And I call it so to say because what we do is that we run particle filter or micro or vehicle simulations. So we simulate over a highway segment individual vehicles. So out of that data, we can then compute the density. So what I plot here to the left is what is the actual density of that simulation of thousands of vehicles. And then you see still there are these black lines. So these are the probe vehicles. So now we do exactly what I was talking about, right? So what you see here is the data that we got from the probe vehicles. And even if we only get data around these lines, you see that between time 0 and 7 minutes, the color coding to the right is quite similar to the one to the left. So the reconstruction of the state is quite good. We can then use that model also to predict into the future, and that is what you see on the right side of the plot to the right there. So we use that model and we predict what will happen the next 2 minutes over this road segment. With the data from the probe vehicle, we have no clue what was going to happen up in the right corner of that plot, because we didn't have any probe vehicle that we actually provide us with that information. So therefore, there is this little reddish corner, as you see there, which is in some sense an impossible thing to solve, right? But we were quite, when we have been running this, we're quite surprised how well it performs this type of method. So notice just that This neural network represents rho, right? And rho is what I'm plotting here. So this is basically, this picture is a picture of that neural network. I had another neural network that I was also considering. That was the neural network representing the velocity function. So this is the blue line you see here is what that map will look like from the data that we use to train that. If you want now to go back to that fundamental diagram that I was talking about, this is the corresponding fundamental diagram, so the flow as a function of density. And you see that we get something like that triangle shape out of this method. So how do we use this now for control? So back to the problem. You see we have one highway, we have a truck platoon, the blue dot there. To the right, along the highway, you see there is some yellowish area to the right, high density. There is some traffic jam there. We would like to see if we can control this truck platoon in order to leverage a little bit the congestion. So let's take a scenario like the one you see here. So in this case, we have space on the x-axis and time on the y-axis. If we are moving now with the platoon on constant speed, it means that we have a straight line there. So this is the red line that you see going through this plot. The yellow area in the plot to the left is congested, is high density, so it's congested area. So you see it starts about 50 kilometers and at time t0. So think that there was a car accident or something happening there. Suddenly it built up big congestion. That congestion is now traveling backwards in space and forward in time, and then at some point is dissolved. That's what we see there, right? In this case here, we don't control the truck platoon. It's just driving through, and you see it go a little bit slower when it travels through this congested area, and then it continues on the other side. So let's now apply the control that I've been talking about. So how can we think about this control? So we want to regulate the velocity. So we say that, okay, the trucks do not just follow the flow, but we can actually change the velocity and go in a slower speed than what we could, right? So what would that correspond to in the fundamental diagram? So if we originally had this blue triangle, if we now constrain it, it means that we basically reduce the capacity of the road. So we continuously would make this triangle smaller and smaller. For instance, so that it takes this red shape over there. So that's the basic idea. And then we can form different criteria of how exactly, what level we should be at there. So if we apply that in this scenario, we get the picture that you see here. So in this case, again, you see the truck platoon is moving through over the highway. It passes now just when the congested area has been dissolved. If you compare the slope of the red line on the right plot to the left plot, you see that the truck platoon is going slightly slower in most of the time there. The color is a little bit lighter above the red line to the right, means that there is a little bit slowdown of the traffic flow. So now the interesting question is, when we're now doing this, it looks in the picture that we succeeded to have less yellow. But is less yellow good for, is that good for everybody? Or is it maybe just good for some here? So did we slow down the total traffic or not? In theory, this is an open problem. It's not so easy actually to analyze that, and I encourage studies of this. Maybe one need to simplify the model that we are considering here a little bit. But we can just illustrate what I'm talking about with some further simulated scenario. So this is a slightly different scenario than previously. You see we have congested areas to the right. That congestion, we can compare when we didn't have that congestion. What time did it take on average for the cars to travel these, in this case, 5 kilometers? So when the congestion is there, it actually was an increase of the travel time of 38%. So now we can apply the control that I've been talking about, and if we apply that, the increase in travel time is just 8%. So it is actually possible with this type of a control to utilize the infrastructure in a more efficient way and actually improve it. I mean, from an electrical engineering perspective, what do we do, right? It's some sort of a low-pass filtering that we do through this PDE that we have described here, right? So we are maybe not surprised that this could be working, but it's quite, to me at least, it's quite fascinating type of different control problem that we maybe see and we are teaching in our courses. So I have one more case study I want to describe, and this is something which is really urgent, and I encourage people to work on. I will be quite brief here, but you know that we have in Europe and US and Asia, at least, we have already electric charging infrastructure for cars. We don't have an infrastructure to charge heavy vehicles. Why? Because for various reasons. To charge a heavy vehicle, if you have seen what corresponds to a supercharger for a heavy vehicle, you know that they are huge, right? So you need much more power to charge a heavy vehicle than your regular car. But that puts some interesting thing now, as you saw in my earlier slide. I mean, you can buy heavy vehicles that are electric today. So we get an interesting problem, so to say, how do we get the deployment of charging infrastructure? And how do we now make that charging infrastructure a business that can, so to say, support not only the automotive companies, the logistic companies, and so on, but also those who provide the power? So there is a lot of opportunities to try to understand where to locate this charging station, how to operate them in the overall freight transport system. So I will just show a little case study that we did here on that for Sweden. So we've been working on where should we place such a charging infrastructure for heavy vehicle in Sweden. So these are the green dots that you will see popping up here. And then we consider now an example where we have, in this case, we say 1,000 electric trucks. We have models for Sweden of freight transport. Where does freight transport, where is the origin and destinations? So we utilize that model, and we then include uncertainty in that model when it comes to travel time and so on. Notice that for a truck, it's typically so that if it's an advanced one, it goes more or less 24/7. If it goes across Europe, if it only goes within a country, it goes during daytime typically. These routes are known. So when the driver sit in the car, right, he knows where he should pick up the goods and where he should be going. So how can you solve this problem? So we have proposed a solution, which is kind of a solution with two types of agents here. So one agent is the individual truck. So we don't think that we can have a solution which is centralized, because the truck or the logistic companies don't want to tell where they are driving or where they have the customers. So we have a solution which is distributed. So the trucks now coordinate with the infrastructure, but not with other trucks. And then the infrastructure can then keep track on what resources it has. So that is the charging station. So we get the solution in this case where we assume that charging stations that provide the service now, the resource, can predict what resources they can give into the future. So in this case, it's over a day here, and this is plots for 4 different charging stations. We count here resource in waiting times. So it's a number of minutes that you have to wait if you will stop charging there. So the solution here again, it's tools from our community. So it's a rollout-based solution. So you have this fairly large multi-agent system, if you want, where each agent now, each truck, along its route, interact with the potential charging station. And then what it does, when it gets these forecasts, these estimates, is that it's now form, in this particular case, we do a worst case analysis. So we form the worst case that it would have, given that it would charge at a particular charging station or not. And then out of that, we get linear programs that the individual truck can solve online, and it can then iterate this as it travels across Sweden now in its mission. So if we look at what such an implementation look like, so now we wake up here in the morning, and you see there start being trucks being driven around. These are not all 1,000 I showed here, but a few hundreds. So they, as you see in the middle plot on the bottom there, you see that's a particular route from going from one origin to destination, charging at a few different places there. So does this work good? Is it good to do that extremely simple, low-cost coordination, right? It's basically nothing changed to a system that we would need to add here. This is very simple coordination. But that simple coordination gives drastically reduction compared to that you just leave the system open. So it's actually in this big study we did about 50% lower waiting times for this. So we've quite simple type of coordination, not doing the most sophisticated type of control, just a rollout type of solution interaction. You get such a benefit. So with that, I would like to give a little conclusion and reason a bit. So I don't know, maybe you were already convinced. If not, I mean, the future is not just more data and more ML or so. The future is to be able in this system to deal with uncertainty. And the uncertainty, we have tools. It's not just an application, because these tools need to be developed so that they can handle that big data and other things. I illustrated here on work that we have been doing on transportation. It's one application area, but there is also others. I talked about that with these methods and much more online and real-time data, combining it with physics-informed type of learning techniques, we can actually build quite more sophisticated models to do control, like in the traffic control example. I talk a little bit about this stochastic forecasting and using techniques from reinforcement learning. And I talked about that actually, if we now are integrating the infrastructure into vehicles, which I very much believe this is what we're going to see, when we do that, we need to have ways of understanding what information we should exchange. In such an infrastructure, it will not be video streaming to everybody, because the infrastructure is not going to be able to support that. Will it be only a state variable, x or x dot? Maybe not. Maybe a set representation is convenient once. Maybe it's sonotops. Maybe it's something else. But I think that we need to think about what are these type of ways of exchanging information in this scenario. So I think that, you know, I would like to communicate to the students, congratulate you that you choose the right area. I think this is where things are happening also in the future in our control community. I think it's not only that we have the mathematical tools, so I think we also have the right spirit. So if you allow me to use one more Latin quote in my talk, I think we know how to proceed quickly, make progress, but also be careful. So with that, I would like to thank you again very much for your attention and for getting up early here on Thursday morning. Thank you.
Thank you so much, Kalle. That was excellent. A little bit of Swedish, a little bit of Latin. What else can you ask for? So that wraps up the Bode lecture part, and I would like to one more time ask Sophie, Luca, and Maria to come up. They've been known as the Dream Team. So again, round of applause for the organizers of CDC.
Thank you, Magnus. So the Dream Team has enlarged today. We are happy that you are joining. So as every day, unfortunately I have to say this is the last day because I was enjoying very much staying with all of you. So the highlights are we had a lunch session from one of our gold sponsor, MathWorks, so please join. And then, as you notice, every day, almost every day, we had some demos, and today it's a demo of a e-scooter. So the idea is that by making this e-scooter be capable of self-balancing and navigating, you can support a micro-mobility solution for sustainable transportations. So please go to the expo area. We change the location, so notice is the expo area, very visible because there are all coffee breaks there. And join the team that is going to show you e-scooters. And then in the evening, please stay with us because there is the farewell, and we were able to have with us that is playing some jazz and swing, the 4 on 6. So this is going to be very special also for us.
Thank you, Maria. So the first thing I would like to announce for those of you who were here the first day, that I'm really happy, we're really happy that the underground torture room has been closed due to inactivity. So that's good news. Now, just some numbers for you. After the huge work of the program committee, the extended one, this conference editorial board, Sophie, and everybody else, we had about 1,400 papers in the program. And we had been warned that we had, to expect about 1.2, 1.3 times that registrations. And in fact, at the end of the early registrations, we had about 1,700 registrants. Now, I'm happy to announce that we currently are at 2,239 registrants, which is an amazing record, with over 150 registrations on site here in Milan. So thanks to you all.
Okay, today it's the last day of the conference. I hope you will enjoy also this day, this last day. And as you have seen this morning, it rained, so Milan is as snow, as you and us. It's every good things have an end, and Milan is also crying this. But okay, enjoy the last day of the conference. Maybe the intruder in the dream team has to say something. Nope. It's okay. No, it's not an intruder, it's a friend.